Okay, let us continue the third part of today's class. Okay, we have calculated that the h of x, entropy of x is equal to 0. Okay, so which is consistent with our interpretation that h of x is a measure of the uncertainty in x. Since there is no uncertainty in this example, so the uncertainty is equal to 0, or we can say the entropy of x is equal to 0. Although we will not show it here, it is possible to show that if capital X is in the set small x1, small x2 to small xn, then capital H of x is maximized when P capital X of small xi is equal to 1 over n for all I, which corresponds to the case where there is maximum uncertainty in the value of capital X, consistent with the interpretation of capital H of x being a measure of the uncertainty in x. One of the problems at the end of the chapter demonstrates this property for the simple case where x takes on only two values. For a more general proof, the Lagrange multiplier method is needed. Okay, a second term that is used extensively in information theory is the conditional entropy, which we denote by h of y given x and define as follows. Conditional entropy is equal to h of y given x is equal to minus summation for all xy p of xy times log pxy of y given x, where p of xy is the joint probability mass function, that is, joint PMF of the random variables capital X and capital Y, and the P capital X comma capital Y of Y given X is the conditional probability mass function, that is, conditional PMF of the random variable Y given a random variable X. We use both of these terms in the subsequent steps. Okay, next in section 2.3 we are going to talk about mutual information. The next term that we define is mutual information. Before we define mutual information, however, it is useful to consider a generic digital communication system, which is depicted in figure 2.1. Okay, in figure 2.1, it shows a generic digital communication system. And in the beginning, there is an information source. And after the information encoder, or after the encoding, we will obtain symbols x1, x2, and so on. And when these symbols are passed through the channel, in the output of the channel, we will get symbols y1, y2, and so on. Then at the receiver, we have an information decoder, and after the decoding, we will obtain the estimated information. As shown, the essential elements of a communication system are an information source. Okay, here, information source. An information encoder. Okay, here, information encoder. That converts the output of the information source into discrete symbols. A communications channel. Here, okay, communications channel. And an information decoder. Okay, here, information decoder, which converts the received symbols into a form that is compatible with the destination. Okay, it is the estimated information. Since we are concerned with digital communication systems, the information encoder converts the information, which could be analog, such as a voice signal, into a finite set of discrete encoded symbols, small x1, small x2, and so on. The encoded symbols are transmitted over a communications channel and are received at the destination as a set of symbols, small y1, small y2, and so on. Okay, like this, x1 and x2 input to channel will produce y1 and y2, etc. In an abstract sense, a communications channel is a system in which the output depends probabilistically on its input. That is, if the input to the channel is small xi, then the output yi can take on different values depending on the properties of the channel. But the value that the received symbol takes on cannot be predicted with certainty, because there are some probability in the channel. This leads to the following question: how much information about the occurrence of an event capital X is equal to small xi is provided by the occurrence of the event capital Y is equal to small yi? That is, if the received symbol is capital Y, which is equal to small yi, how much information has been learned about the event capital X is equal to small xi? The amount of information that is conveyed is called the mutual information, and the abbreviation is MI, which we denote by I of small xi and a semicolon and a small yi, and define as follows. Okay, I of small xi semicolon small yi is defined as log of p of xi given yi over p of xi, where p of xi is the probability of xi of the random variable capital X being equal to small xi, and p of xi given yi is that, given we know that the capital Y, the random variable capital Y is equal to small yi, the conditional probability of capital X, that is, the random variable X, is equal to small xi. Although this definition may not seem intuitive at first, It is straightforward to demonstrate that it leads to reasonable results. The following two examples examine the properties of MI. Okay, example 2.1. Assume capital X and capital Y are statistically independent random variables. In that case, we would not expect the received symbol to convey any information about the transmitted symbol. So the mutual information should be 0, okay, because the transmitted symbol and the received symbol are independent. So reasonably, their mutual information should be 0. Under this assumption, P of xi given yi is equal to P of xi. Therefore, I of xi and yi, that is the mutual information of xi and yi, is equal to log P of xi over P of xi y. Okay. Because according to the definition of mutual information, the numerator in the log term is P of xi given yi, and the denominator is equal to P of xi. And now P of xi given yi is equal to P of xi. So the mutual information of xi and yi is equal to log P of xi over P of xi. Okay, so it is equal to log 1 is equal to 0, which is consistent with our expectation. That is no mutual information here. Example 2.2. Assume the occurrence of event capital Y is equal to small yi uniquely determines the event capital X is equal to small xi. That is, we assume that if we know the received symbol, we also automatically know which symbol was transmitted. In that case, the amount of information we learn about the event capital X is equal to small xi from the event capital Y is equal to small yi is the information associated with the event capital X is equal to small xi itself. Okay, because since we know this event, we can totally know this event, okay, without any doubt. Under these assumptions, we would expect the mutual information to be equal to I of xi, and that is the information of the capital X being equal to small xi. Okay, if the event capital Y is equal to small yi uniquely determines the event capital X is equal to small xi, it follows that P of xi given yi is equal to 1. Okay, because when you know yi, you can completely know the value of xi. So this conditional probability will equal to 1. Okay, thus it follows from equation 2.8. Okay, let us see 2.8. So 2.8 is the definition of the mutual information, and now this is equal to 1, and it is become log 1 over P of xi. Okay, so that is the mutual information of xi and yi is equal to the information of xi, which again is consistent with our intuitive expectation. Okay. In addition to measuring the mutual information between two specific events, such as capital X is equal to small xi and capital Y is equal to small yi, it is also useful to consider the average mutual information between two random variables, capital X and capital Y. We denote the average mutual information by I of capital X, semicolon, capital Y, which is given by I of xy is the expectation of log P of x given y over P of x with respect to xy. Okay, here P of x is the probability mass function of the random variable capital X, and here P of x given y is the conditional probability mass function of the random variable capital X given the random variable capital Y. Okay, so according to the definition of expectation, it is equal to the summation over all possible x and y, and P of xy, okay, it is the joint probability mass function of the random variables capital X and capital Y, and times this term, okay, log P of x given y over P of x. Where for notational simplicity we have eliminated the use of the sub-indices on the random variables. Okay, what does this mean? That is, we omit these symbols. Okay, let me write on this. Okay, it omits that. Okay, px, y. Okay, and here is a y, x, sorry, and here is the x and y, and here is the x, y, and here is the x, and we omit all these red symbols, okay, for the simplicity. Okay, we will explain shortly how the average mutual information is related to the capacity of a communication system. However, before we do that, it is useful to consider two important properties of I of xy, that is, the average mutual information of two discrete random variables x and y. Okay, theorem 2.1. The average mutual information is commutative. That is, I of xy is equal to I of yx. Okay, proof. According to the definition of average mutual information, I of xy is equal to summation xy P of xy times log P of x given y over P of x. From Bayes' theorem, it follows that P of xy is equal to P of x given y times P of y, and is equal to P of y given x times P of x. Okay, I think you already learned it when you take the course probability when you are a university student or undergraduate student. Okay, which implies that P of x given y over P of x is equal to P of y given x over py. Okay, so we can replace this term, that is this term, by this term. Okay, so we can have that it follows that I of xy is equal to summation xy and times p of xy times log p of y given x over p of y. Okay, which is just interchange the rule of x and y in this equation. So this equation is equal to I of yx. Okay, QED. Theorem 2.2. The average mutual information between random variables x and y is related to the entropy of these random variables in the following way. Okay, I of xy is equal to h of x minus h of x given y, and is equal to h of y minus h of y given x, where h of x given y and h of y given x are called the conditional entropies of x and y and are defined as follows. Okay, first, h of x given y is defined as minus summation xy p of xy times log p of x given y. Okay. And second, h of y given x is defined as minus summation xy p of xy times log p of y given x. Okay, here is the proof. Okay, I of xy, according to its definition, is equal to summation xy p of xy times log p of x given y over p of x. Okay, and according to a property of log, okay, let me write here. Okay, log of a over b, okay, is equal to log a minus log b. Okay, like this. So this term can be splitted into two terms. Okay, the first term is minus summation xy p of xy. Okay, p of xy, here p of xy, and log p of x, log p of x. Okay, because p of x is in the denominator, so we must place a minus sign here. And another term is minus summation xy p of xy and log p of x given y, and 2 minus sign will become a plus sign here. Okay, so the first term, you can summation over oy, okay, and you can get this is equal to minus summation x p of x and log p of x, here log p of x, and the second line remains the same. Okay, minus summation xy p of xy times log p of x given y, okay, remains the same here. And we can know that the first line is h of x, that is entropy, and the second line is equal to minus h of x given y. Okay, please see this equation. h of x given y is defined as this equation. Okay, it is 25 minutes. Let us take a break.